And thanks for the invitation. As the others have said, it's really great to be in a live event again and be able to see people, even without masks. So today I'll be talking about some work we've been doing at CERN to try to simplify the way we use public clouds, and we burst our on-premises workloads to external resources. This is an ongoing process for a few years. I've given similar talks with previous states in the past, so hopefully this will bring new things if you watch the other ones. So quick introduction, just complementing what was just said. So I work in the cloud team at CERN. I focus mostly on Kubernetes and containerized workloads. I also do some networking and software-defined networks. More recently, I've been also taking care of GPUs and accelerators, mostly for machine learning workloads. And then in the CNCF, I managed to get CERN into the end-user community of the CNCF. I'm part of the TOC, and for those in academia or research environments, we run a user group that kind of focuses on these workloads, which are a bit special if you compare to the traditional IT in their requirements. So we try to focus on those workloads in this group. It's bi-weekly, so feel free to join the group. So I won't do a lot of introductions about CERN. We're in Switzerland, so it's a known institution here, but I will just highlight that we have like this big accelerator, 27 kilometers, that has this experiment where we basically circulate protons at very high energies, and we make them collide at specific points where we build experiments. The result of all of this is a lot of data. So we have to process today something like 70 petabytes of data every year. We store more than an exabyte these days. And very soon, in just a couple of years, we are introducing high luminosity LHC, which will multiply all of this by 10 times. So we keep looking around for new things that will help us do 10 times more with the same amount of resources, which is always a challenge. This is a picture of the accelerator, and this is a picture of the detector. But actually, for today, because we're in a cloud native day, I actually took Lukasz, which is my usual partner in crime, and we made this video that will hopefully work. Let's see. Whoop, if I manage to go here. And we made a video wearing cloud native t-shirts going underground. So this is the Atlas experiment, the building, and we are walking through, and we have 4 of these. Then when you enter, you have this a nice lift where you check your identity with your retina. Then we have this elevator that will take us to the cavern, which is 100 meters or close to 100 meters underground. It's a pretty large cavern. It's like 40 meters high. And while we go down, I will talk a bit more about it. So the way it works, we collide. We have these 2 beams going the accelerator, and in the detector that we'll see just in a bit, we make them collide. And then the detector is made of, it works like a gigantic camera trying to see what happened. And we take something like 40 million pictures a second, or the equivalent of that. And then we process all of this, and then we have to reprocess the raw data to get to the actual events that will show us what we saw. And the goal is to find something that is outside what we call the standard model of particle physics, to see if we have some sort of discovery. So when we'll get to like 80 meters underground, we'll get out of the elevator. And then you have the tunnels that connect to the main LHC tunnel, but also the ones that connect to the caverns. And we'll go very quickly to the Atlas detector. Again, there will be another retina check, as you have to. This was done very recently, as you can see, by the use of masks. So now we'll go around the tunnel, and then you get to this cavern that, depending on the experiment, can feel very impressive in its size. In Atlas, it's completely full by the detector, so it's kind of overwhelming in the sense that there's no space. So you immediately get to the big magnets. During this video, we actually could go to the 6th floor of the cavern and look at the detector from the top. So this is like wearing cloud native t-shirts. So we took cloud native into the systems, but also we took it to the cavern with this video as well. So it's a pretty impressive thing. I would say come and visit us, but actually with the pandemic, there has been pretty hard to actually take people on the ground. So after this quick introduction, I'll go back to my presentation. It should be somewhere here. Yeah, there we go. Sorry about that. All right, so after the video, I'll talk about what we do with all this data and what we are trying to do with this bursting. So we have a very large data center on premises that has something like 300,000 cores. And then we have a lot of, if you check Magnum clusters, these are the Kubernetes clusters, so we have quite a lot. Not all the resources are using Kubernetes, but it's still pretty large, a significant fraction for the services we run. So 30,000 VMs, so quite big data center, not compared to like the hyperscalers, but still pretty significant. Still, we have these things that make us want to burst, and things like international conferences where all the physicists want to do their analysis before they publish their papers, or things like GPUs that became really popular with machine learning, and that we don't have that many. We have a lot of CPUs, but actually not a lot of GPUs on premises, and then things like TPUs and IPUs that we just can't have because they are dedicated accelerators offered by the public cloud providers. And then, for example, when we buy new GPUs, we want to evaluate the different models with our workloads, and getting access to those resources can be a bit challenging. So actually accessing them in the public cloud and being able to run our workloads there, it's very useful. And then we also have use cases where we want to do disaster recovery, maybe put some backup data on the cloud. So we did some previous talks about scaling, showing that we can actually scale to the needs we have. So back in 2019, we did this demo where we processed 70 terabytes in 5 minutes for an analysis of the Higgs discovery that usually would take like a day. So that shows how much being able to scale quickly can have an impact in our own workloads. But still, this was kind of like a stunt. We could do this once, but can you actually have a production deployment where people are submitting their workloads regularly? What we showed here is that we started by having a stack on premises that was based on Ceph, Kubernetes, like Redis, and then Jupyter, and then we just directed those workloads to the equivalents using in the case, the Google Cloud, and with very minor modifications, mostly because of the scaling needs of the infrastructure, we could replicate the workload. So that is very encouraging. And we did this demo where we would build a Higgs plot discovery live on stage in 5 minutes. So that was pretty cool. Now, there's a lot more to it when you start putting this in production. First, we want to support multiple cloud providers. We don't want to be locked into a single cloud provider. Even if we like them a lot, it's always a good thing to have a backup one. Then our users don't really interact with Kubernetes directly usually. They will have their tools in-house. It can be anything. It can be like analysis facility, it can be GitLab runners, it can be anything. So we need to integrate those with the infrastructure that is provided by this stack. Then we want to centralize the monitoring from these resources into our usual monitoring, the logs with our log collection, sending logs to the security team for evaluation, the tracing. And then you need to do proper accounting, costing. Anyone that has tried public cloud and gave too much freedom saw the bill very quickly. So this is a lesson that is very, very easy to learn. So the first step is to see what's around there. So cloud native, the landscape is massive. So whatever you want to do, you'll probably find something. The problem is that you probably find multiple options. So you start to have to evaluate. So hopefully this is a talk that will give some feedback on our experiences. The definition of cloud native is also can change. So from our perspective, the most important part is this idea that there are loosely coupled systems that are resilient. This is very important, and we are used to this because we've been doing distributed computing for quite a while, and we are used to having distributed centers where we run our workloads that are not so well maintained in many cases, so we need to be very good at handling failures. So this is the landscape. This is an old picture. It gets bigger every day. There's some criteria here, and in the TOC, this is one of the things that we have to do, which is to understand at what stage the project is in terms of maturity and support by end users. So this criteria is really a very good tool for end users to choose products. So you have different levels of maturity, starting with sandbox, which is the entry point, and then there's an incubating stage, which already implies some review of the projects and gives some confidence in terms of long-term support and like diversity in terms of development in the project and support from different companies. And then finally, the graduation stage, which is where like things like a complete and independent third-party security review would happen, and then like confidence increases even more. So based on this, we started looking at our deployment. So what we want is to have something that is fully centralized and managed centrally. We don't have to deal with different tools in different clouds. And this implies not only the applications that are being deployed, but also the clusters themselves. So what we wanted was to have a definition of which resources should be running where, and this would also manage with the management of the clusters in the different public cloud providers. We also want to support multiple clouds, but also multiple regions and zones, and I'll mention why this is also important. And then have these base services that do all the base functionality for the infrastructure and all the collection centrally. This is also something that should be, as far as possible, common across the multiple clouds. And then the way for the workloads to be deployed, and we need to support whatever our application developers and service managers chose. So in most cases, I would say that we are choosing Helm, but we have cases where it's customized, or we have cases that it's just plain YAML files. So dividing this into groups, we have what I call the underlay, which is basically the clusters, the Kubernetes clusters that are running on the different clouds. Then we have the infrastructure layer, which is the base services like Prometheus, the registry, maybe FluentD for the logging, and a bunch of services that we require internally as well. So one, for example, for software distribution, we use containers, but we also have a way to access packages using a file system, a read-only file system that we call CERN VMFS, CVMFS, which is basically a hierarchical squid cache deployment where the top level is CERN, where we push the packages, and then a bunch of squid caches that just pull on request from these places. So we need to deploy these components. There's a couple like this from our stack. And then finally, the services and applications. So we chose to manage all of this. We are full into GitOps. We were already into it with Puppet as well in the previous deployments. So this is actually a very nice way to break the barrier to start working with Kubernetes for service managers. They don't have to learn all the details of how to do Kubernetes, or how to understand all this ecosystem. They just need to understand how things are defined in these files in the central repository. This is a nice way to get them doing something, and then gradually they will learn the stack as well. This really hides most of the complexity. And this is an example. So the application is called Metar, but it's irrelevant here. But then you have this infrastructure, the underlay, the infrastructure, and then services and workloads. And these are grouped together. And then as you dig down, you will find the details. So this is how it looks, the deployment. So we support all the clouds. And I mentioned that we support multiple public clouds, but we also support multiple regions very easily. And the reason for this is, for example, if we look at the GCP examples here, you won't get GPUs, all the models that you might want in all the regions, or even more importantly, you might not have the capacity of GPUs in one region that you require for a certain moment. So it's quite important for us to be able to shift these things very easily. And the way we do this is that we created these sort of YAML definitions where we say how each cluster should look like. and then the system will just deploy the clusters and manage the node groups for us. It includes things like enabling auto-scaling with a maximum amount so that we allow the cluster to manage, self-manage in terms of resource allocation. So we do have deployments like this. You can see GCP, we have GPUs and then TPUs. And then we need AWS. We use also for GPUs, but it's the only one providing ARM resources. And we have push for supporting ARM as a base for our workloads. So things like building packages for ARM, we needed these resources. We didn't have them immediately at CERN. We started using the AWS for this kind of thing. And I will explain how this is integrated. And then Azure, we also use for GPUs, but they have also access to these IPUs, which are quite interesting as well for accelerated workloads and machine learning. So yeah, the details are here. It's a nice way to describe like the full, what is quite complex infrastructure across multiple clouds, multiple regions in just a YAML file. For this, we rely on a component called Crossplane, which is kind of more recent in the ecosystem, but it just got into incubation. And what it allows us is to define the clusters themselves as Kubernetes resources. So this is a different approach from, for example, using Terraform. It has advantages. It means that we manage the clusters themselves just as any other resource in our infrastructure. So there's a big plus there. It also means that we have a central cluster where all this is tracked. If I want to see the status of the infrastructure, I have a central point where I can see it, and it feels very familiar. So it allows us that their support. They have what they call providers. Their support for GCP, AWS, and Azure as well. One thing that we started writing, because on premises we have an OpenStack cloud, we actually started writing a provider for OpenStack so that even our on-premises resources will be integrated into this system. We won't use it just for the public cloud stuff. So this is the project. I will let you investigate a bit, but I'm more than happy to talk about it because I find it quite interesting. It's touching an area that was kind of left outside the cloud-native pure way, or at least in the Kubernetes ecosystem, and it manages. In this case, we manage clusters, but actually you can manage any resource on these different clouds. So this is how it looks in our Argo CD monitoring. We have all the clusters, and then you will see all the node pools that each cluster is supporting, and then you can dig down and see what's the current configuration, what the system decided. It does reconciliation constantly. So if, for example, there's an issue with some node or deployment, it will also give you feedback on this centrally. So the second layer after the underlay is the infrastructure, as I mentioned. So this is in this area, what we want is to have a central stack at CERN, and then integrate everything for the external resources with our central stacks. And this is important, for example, for the registry. We want to have a central registry for container images, Helm charts, everything that is managed by us and tightly controlled by us centrally. And then we deploy registries on all the instances, all the clusters we run outside, and they are configured similarly. And they are usually configured with two things. One is that we configure pull-through caches so that you don't get images from anywhere. You have to pull them through the local registry, but coming from the CERN registry. The other thing is that we actually have replication rules that basically the CERN registry, when a new cluster is added, has a new replication rule that we push popular images immediately to those clusters to make them available right away. The same is true for Prometheus. So we have a Prometheus instance on every cluster, and then we use Thanos to do the distributed queries across all the clouds and clusters. And then we have a central dashboard where we can navigate this all this information. Another component that we also deploy is the Open Policy Agent. This is important for things that we already do internally on premises, which is things like enforcing that only the certified registry is being used for the images, or that all the workloads have the labels they should have so that we can do accounting and costing. We use the OPA gatekeeper, which is a easier to use way of configuring the policies. But in this case, we also use it for saying only this type of workloads are allowed to run, for example, on GCP, or only this user is allowed to run on Azure. And we can define these policies centrally, and then they are propagated to all the clusters in the same way as everything else. And then I mentioned CVMFS, and then we replicate all of this. I will just have one slide on the registry, because this is something that is still evolving. This is what we do internally at CERN, and this is also what we enforce on the clusters. And this is using some projects that I would like to highlight. Liz actually mentioned Falco this morning, especially for the eBPF. They also have a custom kernel module, but I think the transition will be to eBPF as well. And but basically what we want is to have policies that enforce that all the images have gone through our registry, have been checked for vulnerabilities. In this case, we use Trivy. We do have a way to manage allow lists to like ignore some of the CVEs per project or not. We sign the images, and then we have OPA basically enforcing these policies in the cluster and in the public cloud and the clusters. There is one question, which is like, you passed all the CVE checks, you deployed your application, it's running. Now there's a new CVE, what happens? So we have an internal tool right now alerting about these cases. But the other part is that we also want to check what's running at runtime to not allow, for example, people to change the image, pip install, whatever, at runtime. We don't want most of the users shouldn't be allowed to do that. So we do these checks also using Falco. This is an example of, so for the registry, we use Harbor, and this is an example of the rules that are added to Harbor when clusters are added. In this case, it's a push replication, so that we pre-populate the registries with all the images we need. This is a view of the Prometheus dashboard for monitoring of GPUs. Actually, monitoring the workloads, if they're efficient or not, usually needs a lot more metrics. We do have a way for applications to express those metrics and collect them centrally. It's not that easy to sometimes expose to the end user. But another way for us operators to see is actually GPU usage, like how much power is taking, what's the temperature. This is actually a nice way to say this workload is actually using the GPU, or we should contact the user and improve it. And then you can just filter by cluster, try to dig down into the details. All this data is the standard Prometheus NVIDIA operator metrics get collected in a central place, and then you can go through them. The next, for the rest of the talk, I'll talk about the use cases that we run on top, and to try to give an idea of how to integrate those. Because once you have the infrastructure is nice, but your end users will probably not kubectl create and my application using YAML. Most of the physicists don't care about that, and they don't want to care about that. So it's quite important to help them do the transition. So the first use case actually that we ran there was evaluating the efficiency of physics computations using GPUs, different kinds of GPUs. And what we asked the user was, can you give us a Docker file and we'll manage this for you. And what we did, they gave us, for different use cases, Docker files. And we just told the system, OK, run this across all the GPUs. And in this case, it's just the GCP ones. And you can see very quickly, we get, without having to buy like all this hardware, we get very quickly an idea of what's the performance of your workload in these different GPUs. First, one thing that came out immediately is that, for example, the A100s, which are very recent, the improvement was not as expected, which triggered some review of the code by the user, and eventually improving that usage. So this gives us like a very quick picture. The deployment is also publishing metrics on the performance. Then it all gets collected by Prometheus, centralized, and we can see in our CERN dashboard what was the actual performance of this workload. The other thing that is also important is not only, like in this case, it's actually probably not the best example, but one thing we care is performance, like events per second is usually our metric. But when you start using the public cloud instead of on-premises resources, you're not trying to maximize usage, you're trying to spend as least as possible. So in fact, some of the workloads, they might be a bit better in a certain GPU, let's say, but actually, if you don't have a time limitation or you're not restricted by time, you might want to use a less performant GPU that is much cheaper and will give you the same number of events in a slightly longer period, but for less cost. So all these things kind of are taken into account as well. So the second example I'll give, if you're running CI/CD, it's a really nice way to get workloads with a really familiar interface to all our users. And then by just configuring, in this case, GitLab runners across all our clusters in different types of resources, we basically pull from a central queue and we render workloads. And because we have this infrastructure services already set up, like this access to CVMFS, the workloads run there and they pretty much don't notice that they are somewhere else. This is also why auto-scaling of the node pools is very important. We usually auto-scale to 0, meaning if there's no jobs requesting these resources, we don't pay. And then as jobs come, there are nodes being spawned. There's a slight delay, a couple of minutes. In some cases, it can be even less for the job to start, but this is usually acceptable. This allows us to expose with an interface that everyone uses at CERN, a huge amount of different types of resources. I list here GPUs. We also started offering TPUs, and this was like a God gift to build stuff in ARM. So people were really happy to suddenly get ARM resources like this. So an example of like a test job that basically tries to run a GPU job across all our types of GPUs that we support, also TPUs, and then collects the metrics. This is a similar one for a TPU deployment. If you've done some TensorFlow to run TPUs, there's a bit of boilerplate, but you can easily access a TPU without having to understand anything of how to use the Google Cloud. Just need to know GitLab at CERN, and you're running your workload on a TPU. This is an example of running ARM. In this case, we're just running a benchmark job. And again, like we can go to the system, see where the job was running, and then go to the node monitoring and tell the user, this is the performance of your application running on an ARM node in the AWS. The last use case I'll mention is machine learning. So this is the kind of most exciting these days, I would say, because they need like tons of resources. This example is doing fast simulation. So one of the big requirements we have, in addition to processing raw data, is to have simulation data that kind of tells us what's expected. If there would be, for example, a new discovery of a new particle, this is how it should look like. And then we can compare the raw data against the expectation. Generating this simulation data is extremely resource intensive. It's been traditionally done with CPUs, but recently we started using GPUs and even TPUs. And you can see, like, we can very quickly access like a huge amount of GPUs. In this case, we managed to run up to 128 GPUs in parallel for a single workload, which is quite nice using this multi-worker mirrored strategy. And again, by having this common infrastructure, way of collecting metrics and all of this, we can build these bots very easily for the end users. As long as they put the proper labels in their workloads, they can see how it propagates. In this case, it was a particularly well-behaved workload, so it's nice to show in presentations where we had pretty much almost linear scaling up to 64 GPUs and then slightly less at 128, but still like really impressive. And what this means is that for basically a flat cost running on the cloud, I can have my results 100 times faster. So this is something that gets physicists really excited, and that kind of matches our requirement to do 10 times more with the same in just a couple of years. So this is the sort of thing that we are trying to do also by accessing external resources. Yeah, you can also see like TPUs also give really nice opportunities here. So one thing that I would highlight also here is like when you start using the public cloud, one thing that is quite important is cost, of course. Preemptables are super interesting. And this summarizes a bit the challenges that we had while we were doing this. We run at pretty large scale often. So CPUs kind of feel infinite most of the time, I would say, at order of tens of thousands of cores, even single region. It doesn't seem to make a bump, and we run, no one complains, and that's it. When we start talking about GPUs, it's not quite the same because we want to do preemptables, which are incredibly cheaper. So we want to use preemptables. Our workloads are really nice at this. When we start using like thousands of GPUs, it's sometimes not possible to do preemptables. So it's really important to stay flexible on how to deploy workloads across multiple clouds, but also across multiple regions where maybe preemptables, if you can split the workloads like this, you'll probably have a better chance of being able to run the full thing in preemptables instead of having to run with on-demand instances. Then the other thing we learn is that the Kubernetes offering, like all the public clouds, provide really nice managed Kubernetes solutions. There are slight differences in expectations. Maybe the cluster creation time will be a bit slower in some of them. The configuration of GPUs and autoscaling is also not super consistent all the time. The tooling, if you need to debug something directly, then you will have to use their tooling at some point, and this can also be a bit of a change, but overall, it's pretty comfortable to go from one to the other. And then I won't go in detail because I could give like 2 talks about this, but regarding costs, I would just highlight that, yeah, for us, because our workloads are really nice for this, like preemptables or spot instances are amazing. If you can use them, do it, because they're much cheaper. Again, can get challenging at thousands of GPUs. There are things like sustained use discounts that are pretty, like for free, you don't even have to negotiate, you just get them. One thing that everyone using these kind of resources knows is that ingress is for free. Egress can be extremely expensive. For our workloads, the egress costs can be something from 5% to up to 30% of the total cost of running an operation. We do need to bring a lot of data back. So the last bit I will talk about is that because cost is so important, we started looking at more streamlined way to cover costs. So we've been experimenting with a tool called KubeCost. There are others in this ecosystem, but the idea is really to build on the Prometheus stack we have and be able to, from that, get all the billing down to the individual workloads. You can see, like, you can add labels that will group the workloads all the way to like teams, departments, cluster, whatever, clouds. But what we want is also to be able to tell users, like, your workload costs this, and then compare that to our view of their efficiency to maybe work out with those teams to improve that. This is something that is ongoing. It's not trivial, but the goal is really to go all the way down to individual workload costing. So the things we are doing, as I mentioned, individual cost reporting is something we are working on improving. And then the second part is all that I talked about are traditional physics applications that are what we call high throughput computing, HTC, meaning that they don't really have any kind of requirement for tight coupling between the independent jobs in a big workflow, for example. This means that they are completely independent. If they fail, we can retry them. The total result does not really depend on connectivity between the different jobs. We start having workloads where this will be the case. So, for example, the workflow, the use case I mentioned for machine learning, it works without any kind of like fast interconnects or something like that. We have others where the models are so big that actually you need some sort of special hardware that the public cloud providers do offer, but that restricts us in terms of how we can use the resources across regions or across public clouds. Also, some services we have needed low latency between on-premises and the remote sites. So service meshes is something that we've looked at because of the Kubellow deployments that we use for machine learning. It's something we are learning. It's not an easy thing to do if you have really tight interconnectivity. Our approach has always been that we try to deploy. If there's requirements are there, we kind of deploy the workload in a single place and do it all there. So something that will come. So basically, before we go to questions, I would just summarize this as today it's still an evolving infrastructure, but we are already managing tens of clusters in this way. Central Git repository, everyone does changes there. Everything is reviewed in a central place. Helps with onboarding, helps with versioning all the infrastructure. And we do this across multiple public clouds. If you add a cluster to the configuration, you can count on, depending on the infrastructure you're using, 10 to 15 minutes to the cluster being fully available to the production workloads. Again, with auto-scaling node groups, it doesn't mean that the resources are available, but the cluster is fully configured with all the services we need. As soon as workloads are allocated there, the node pools, node groups will start spawning nodes. Auto-scaling is something that is incredibly easy with this kind of infrastructure compared to what we had before. Because everything is declarative in a central place, actually, we let the systems make the decisions about how to do auto-scaling. We don't have to do any kind of plumbing to check queues, queue sizes, expose metrics, write any kind of special tooling. We can delegate this to the stack that we deployed. And then there's also an advantage to having a very similar infrastructure stack across all the public cloud providers. The Kubernetes API and similar projects kind of became our entry point to this external world, which is also what we use in-house for a lot of things. So it's kind of making life quite a bit simpler. And I'm more than happy to answer any questions that you might have.